Have you ever wondered what really passes through our solar system when an object arrives from deep interstellar space? Every so often, telescopes catch something on a strange path, moving too fast to be born here. One of those visitors is known as 3IATLAS, and some researchers think it may have released tiny companion objects along the way, mini fragments that quietly slipped past us. Astrophysicist Avi Loeb has argued that the data hold clues we have not fully faced yet. Are these just odd rocks, or signs of something more deliberate? Tonight, here on Sleep Astronomy, we will walk through the evidence, step by step, and see what we can honestly say. If slow, careful journeys through questions like this fit your pace, a gentle like and subscribe helps others drift here too. For now, settle in and let's follow 3IATLAS through the dark. On November 19th, NASA released images they had been holding for weeks. They show features around the object, known as 3IATLAS, that current comet models do not easily explain. In a 45-minute briefing, the agency described 3IATLAS as a comet, ice, and dust from another star system behaving in familiar ways. Yet some of the pictures suggest a more complex story. Amateur astronomers then reported something very unusual in images from November 20th. A clear X shape. Two narrow jets appear to shoot sideways from the comet, almost perpendicular to the usual line between the comet and the Sunday. Each jet seems to stretch for about 1 million kilometers from the center, more than twice the distance from Earth to the Moon. If these features began when the comet reached perihelion, its closest point to the Sun, on October 29th, then the material that forms those lines has been traveling at about 500 meters per second for roughly 22 days, without slowing or drifting off course. Astrophysicist Avi Loeb has worked through these numbers and asks whether we are seeing simple jets of gas and dust or the trails of many separate objects released near the Sun, each one keeping a steady path that loose ice fragments would not maintain. To follow that question, it helps to look at the timing and the observations. On October 29th, 3IATLAS passed perihelion at a distance of about 203 million kilometers from the Sunday. Temperatures there should have heated the surface enough to strip away volatile ices in a fairly smooth, symmetric pattern. Instead, when the comet emerged from behind the Sun weeks later, it showed multiple jets pointing in several directions. For much of this period, official information from NASA was limited. The deep space antennas still operated, and spacecraft continued to collect data, but public updates almost stopped. Just when 3IATLAS was passing through a critical part of its path in the inner solar system, official channels were quiet, and people filled the gap with their own ideas and theories. On November 19th, NASA held a detailed press event. They presented what their network of spacecraft had recorded. There were images from the Mars Reconnaissance Orbiter taken on October 2nd, when the comet was about 19 million miles from that spacecraft. The closest any NASA asset came to 3IATLAS. There were observations from the MAVEN mission showing the cloud of hydrogen, the coma of gas and dust around the nucleus, glowing in ultraviolet light. Other missions added more views. Together, these datasets formed a broad survey of an interstellar object passing near a star. Throughout the briefing, one message repeated. NASA officials said that 3IATLAS is a comet. They said that it looks like a comet and behaves like a comet, and that all their evidence supports that view, with the extra detail that this comet comes from outside our solar system. They also said they have not seen any technological signatures, nothing that would suggest an artificial origin. The word comet appeared so often that it began to sound less like a simple label and more like reassurance. While that briefing took place, Avi Loeb was studying the same images. He focused on what the pictures actually showed. The Mars Reconnaissance Orbiter images, the sharpest NASA has, show 3IATLAS as a short streak of light spread over several pixels. Because the spacecraft was moving slightly during the 3.2-second exposure, the light is blurred. Even so, the glow around the streak is not smooth. A faint X pattern is visible in the surrounding material, a cross shape in the coma. In simple terms, there seem to be 4 main directions for the escaping material, not just 1 or 2 as in standard comet tails. Earlier amateur images from August and September hinted at the same X shape before the comet passed behind the Sunday. Seeing it again in data from a spacecraft orbiting Mars suggests that this structure is real, not a trick of perspective. Tom Statler, the lead scientist for small bodies in NASA's Planetary Science Division, highlighted that 3IATLAS has probably been drifting in interstellar space for a very long time and may come from a planetary system older than our own. That would make 3IATLAS a sample of very ancient material, older than Earth and the Sun themselves. These ideas help explain why scientists are eager to study this visitor, but they did not answer the specific questions raised by the X pattern or by the jet directions. 3 days after the press event, new observations added more detail. On November 20th, 3 experienced astrophotographers, Michael Yeager, Gerald Riemann, and Enrico Prosperi, stacked 20 exposures of 100 seconds each. This technique makes faint features stand out much more clearly than in single images. Their result was a sharp view of 3IATLAS with the X pattern visible in a very clear way. 2 thin, straight jets extend roughly perpendicular to the line connecting the comet and the Sunday. In their processed image, one jet points up and the other down, each reaching about 1 million kilometers from the nucleus. According to current models of comet behavior, structures like this are difficult to explain. When a comet moves toward the Sun, its surface warms. Ices of water, carbon dioxide, and carbon monoxide turn directly from solid to gas. This process, called sublimation, drags dust off the surface, and the flow of gas and dust produces thrust. This is why comets sometimes show small accelerations that cannot be explained by gravity alone. The important point is that the jets produced in this way are usually aligned roughly with the direction toward or away from the Sunday. They are not expected to be neatly perpendicular to that direction. They are not expected to stay in perfectly straight lines for 1 million kilometers without spreading out, and they should not keep a fixed orientation if the nucleus is spinning. Rotation is central to this problem. In July and August, observers measured the rotation period of 3IATLAS and found a value of about 16.16 hours. Several groups confirmed this. If that spin continues, any jet coming directly from the surface should sweep out a curve on the sky. Over about a month, the time it would take gas and dust to travel 1 million kilometers at a typical speed of around 400 meters per second, the comet would complete roughly 45 rotations. A surface-tied jet should then produce many overlapping arcs, not a single narrow beam. The November 20th image does not show dozens of overlapping arcs. It shows 2 straight, well-defined jets. Based on this, Avi Loeb outlined 3 broad possibilities. The first is that the jets are fully natural, but reveal a kind of comet activity that forces scientists to rethink how jets form and stay focused. The second is that the jets are not gas and dust streaming directly from the surface, but the evaporated trails of fragments that broke away from the main body and are now moving on their own paths. The third, more speculative, possibility is that the jets are produced by controlled thrusters, some form of technology that maintains a steady orientation for navigation. Loeb is careful to say that the simplest explanation is still that at least one of the straight features is a streak from an artificial satellite in Earth orbit passing through the field of view. However, he also points out that the same X shape appears in the Mars Reconnaissance Orbiter image from October 2nd, taken from Mars orbit, where no Earth satellite can interfere. If one image is affected by a satellite, it is a strong coincidence that it matches a pattern already seen in a completely separate dataset from a spacecraft roughly 30 million kilometers away. This leads to a central question. Did 3IATLAS release additional objects near perihelion? Did some kind of breakup event, whether gentle or violent, send pieces away at speeds of about 500 meters per second, leaving behind long, straight trails? Calculations show that if the jets began forming around October 29th and now stretch for about 1 million kilometers, then whatever produced them has been moving at that average speed for about 22 days. That is much faster and more sustained than standard outgassing flows from surface ice. It suggests motion with significant momentum, either from fragments thrown out by a powerful natural event or from a process we do not yet understand. How we interpret this depends on how strongly we believe that 3IATLAS is following the usual rules. Comet physics sets expectations for how ice and dust respond to sunlight, and most comets studied so far fit those expectations well enough. The two previous interstellar objects also give a mixed picture. In 2017, the object called Oumuamua showed no visible comet-like activity and remains one of the most debated finds in modern astronomy. In 2019, the interstellar comet Borisov behaved almost exactly like the comets we know from our own system. 3IATLAS began its visit looking fairly standard, and that calmed some early worries. Since then, each new observation has added at least one more puzzle. Avi Loeb has been keeping an anomaly catalog, a list of features of 3IATLAS that do not sit comfortably inside the basic comet model. As of November 15th, there are 12 separate items on that list. Any one of them on its own might be explained as a rare but natural variation. Taken together, they describe something that may be the most unusual natural comet yet observed, or something else entirely. We can look at these 12 anomalies one by one, because each one sits on top of the last. By the time we reach number 12, it is easier to see why this object has drawn so much careful attention. The first anomaly concerns the path of 3IATLAS. It moves on a retrograde orbit, opposite to the motion of the planets. That part is not surprising for an interstellar visitor. Such objects can come from almost any direction. What is unusual is that its orbit lies within about 5 degrees of the ecliptic plane, the thin, flat sheet where the major planets move. The chance of an interstellar object arriving that closely aligned by accident is about 0.2%, roughly 1 in 500. On its own, that is not impossible. But the ecliptic plane is not just any plane. It is where the planets are, and where most of the interesting activity in our system happens. If someone wanted to design a path to study several planets in one pass, the natural choice would be to travel near that plane, not at a steep angle far above or below it. 3IATLAS came in almost exactly that way. The second anomaly is the anti-tail. In July and August, and again in early November, 3IATLAS showed a jet of material pointing roughly toward the Sun instead of away from it. Comet scientists do know about anti-tails. They usually appear when larger dust grains lag behind a comet along its orbit and, from our line of sight, look like a tail pointing forward. When you work out the geometry, the effect disappears. For 3IATLAS, the analysis suggests that the sunward feature is real material flowing against the direction of the solar wind. For this to happen, the gas and dust must be thrown out with enough speed to push against that wind, which means a significant amount of energy, more than simple sunlight on a cold surface is expected to provide. The third anomaly is the combination of mass and speed. The nucleus of 3IATLAS may be about 1 million times more massive than the object known as Oumuamua, and about 1,000 times more massive than the interstellar comet Borisov. Yet, it is also moving faster than both. The odds of an interstellar object being both unusually massive and unusually fast are estimated to be less than 0.1%. Once again, not impossible, but low. Each unlikely feature by itself could be a random outcome. When many such features appear together, people start to wonder whether they are seeing pure chance or some underlying pattern. The fourth anomaly involves timing and geometry. 3IATLAS reached the inner solar system at just the right time and on just the right path to pass within tens of millions of kilometers of Mars, Venus, and later Jupiter, while remaining hidden behind the Sun from Earth during its closest approach to our star. It passed closest to Mars on October 3rd at about 29 million kilometers, close enough for orbiting spacecraft to take detailed images. It then moved behind the Sun from Earth's point of view and reached perihelion on October 29th. In March 2026, it is expected to pass within about 54 million kilometers of Jupiter. If someone wanted a grand tour path that visits several major planets while staying out of Earth's direct view during the most active phase, this is close to what they might choose. One estimate puts the chance of this particular geometry at about 1 in 20,000. Avi Loeb is not saying that these probabilities prove design. He notes that very unlikely patterns happen all the time in a large universe. For example, if you shuffle a deck of cards, the chance of getting that exact sequence is about 1 in 10 to the power of 68. Yet you always get some sequence. The real question is whether the specific pattern we see here looks more like intentional planning or like the natural variety produced by billions of objects moving on many possible paths. The fifth anomaly is the early activity. 3IATLAS was already active, forming a coma, when it was about 6.4 astronomical units from the Sun, out near the orbit of Jupiter. At that distance, sunlight is usually too weak to turn water ice directly into gas at high rates. For strong activity there, the comet either needs a different mix of ices, with more volatile materials like carbon monoxide and carbon dioxide, or an internal heat source. These gases are known in other comets, but the strength of the early activity in 3IATLAS seemed higher than expected. The sixth anomaly is the lack of breakup. Many comets crack or fragment as they heat up near the Sunday internal stresses from expansion. The weak structure of rubble pile bodies and tidal forces can all pull them apart. Borisov did not fragment, which was somewhat unusual, but still within known behavior. 3IATLAS also stayed intact, even though it passed within about 1.44 astronomical units of the Sun and clearly experienced strong outgassing based on its jets. Images from November 11th taken by David Jewett and Jane Liu show a single central body after perihelion, with no obvious pieces trailing behind. This suggests either an unusually strong structure or an internal makeup very different from typical comets. The seventh anomaly is the brightness curve. As 3IATLAS approached the Sun, it brightened in a way that did not follow the usual rule. Comets typically follow a power law, where brightness increases with decreasing distance from the Sun, often with an exponent between -2 and -3. 3IATLAS brightened with an exponent of about -3.9, more steeply than normal. Then, after perihelion, its brightening curve flattened, and it continued to get brighter even as it moved away from the Sunday. This is the opposite of what simple heating models suggest, and points to ongoing, or even increasing activity after closest approach. The eighth anomaly is the ratio of dust to gas. Spectra of 3IATLAS show familiar comet gases: carbon dioxide, water, carbon monoxide, and carbonyl sulfide. The mix itself is not strange, but the amount of dust compared to gas seems lower than usual. In other words, the comet appears gas-rich and dust-poor relative to many comets we have studied. Gas-rich comets tend to be more active and more variable. Small changes in sunlight can cause large changes in the strength of their jets, making their behavior harder to predict. The ninth anomaly involves nickel. Some observations indicate the presence of nickel in the material around 3IATLAS. Nickel can appear in cometary material, but usually only in very small amounts. If this detection is confirmed, it could mean that 3IATLAS formed in a different kind of stellar environment than most comets we know, perhaps around a star with a different metal content than our Sun, or that its material has been processed in a special way. For an interstellar object, a different formation history is expected, but the details of the nickel signal are still important. The 10th anomaly is the non-gravitational acceleration. As 3IATLAS moved toward perihelion, its orbit shifted slightly away from what pure gravity would produce. This kind of behavior is normal for an active comet. Jets of gas act like small thrusters, but the amount and direction of this extra push have to match the pattern and strength of the observed jets. In this case, the jets after perihelion point in several directions: toward the Sun, away from the Sun, and roughly sideways. Loeb's estimates suggest that to match the measured deviation in the orbit, the total thrust from these jets would require that more than 10 to 20% of the comet's original mass was lost near perihelion. That is a very large fraction for a nucleus that still appears whole. The 11th anomaly is the persistence of the anti-tail. The sunward feature, first noticed in July, remained visible into November. That means months of sustained outflow in a direction that is hard to maintain. Images from November 15th, taken from a telescope in Thailand by Tiasak Talawang, show a strong anti-tail, along with two more ordinary tails. There are three clear directions for the material. One possible explanation is that 3IATLAS is releasing unusually large dust grains, with sizes around 100 micrometers. A grain that large can be about 1 million times more massive than a tiny dust particle only 1 micrometer across. With that much mass, these grains could keep moving sunward against the solar wind and form a visible anti-tail. But for this to happen over months, the comet would need a mechanism to keep producing such big particles in large numbers. That is not typical behavior for comets, which usually do not throw out boulder-sized material in a steady way for so long. The 12th anomaly is the one that has most recently drawn attention. It concerns the way the jets hold their shape despite the comet's rotation. As measured in July and August, 3IATLAS rotates once every 16.16 hours. There is no known process that would suddenly stop that spin. Yet the jets seen in images from November 9th by Frank Neblung and Michael Buchner do not show the expected twisting or gaps. They extend beyond 1 million kilometers as narrow, well-collimated beams. At typical sublimation speeds of about 400 meters per second, it takes about 1 month for material to travel that far. During that time, the comet should complete about 45 full rotations. A jet tied directly to the surface should then be broken into a series of small arcs or segments, showing where the source turned away from and back toward the Sunday. Instead, the jets look smooth and straight. Loeb offers three main ways to think about this. The first is that the jets are the evaporating trails of fragments thrown off in a single explosive event. If large pieces were launched away from the nucleus all at once, they would travel along straight paths, and the gas and dust they release as they warm would naturally line up along those paths. This is a natural explanation, but it clashes with the observation that the main nucleus still appears intact and does not show obvious signs of a major explosion. The second is that the jets keep a fixed direction because the vents that feed them switch on and off in a special pattern. If a vent becomes active only when it faces the sun, and if the rotation and orbit line up in just the right way, the same vent could light up at the same orbital position again and again, tracing what looks like a straight jet. This requires fine-tuning, but in principle, it could happen. The third possibility is that the jets are produced by technological thrusters that hold a stable orientation for navigation. Loeb includes this option not because he claims proof, but because, from a logical point of view, it is one of the possible ways to get such steady, straight jets. He argues that to rule out this idea without looking for evidence would itself be unscientific. This is one source of tension with many of his colleagues. For some astronomers, simply naming the technological hypothesis feels like stepping into the territory of conspiracy thinking. They prefer to state that 3IATLAS is a comet and leave it at that. Loeb's position is that science should follow the data, even when the data are uncomfortable, and only remove options after they have been tested. The X pattern seen on November 20th adds weight to this discussion. If the sideways jets are real and not caused by a passing satellite in Earth orbit, then they do not match any standard explanation for comet jets. They are close to perpendicular to the sun direction. They extend for about 1 million kilometers. They show no clear sign of being cut into pieces by the comet's spin, and if Loeb's reading is right, they may mark the paths of many separate objects that left 3IATLAS near perihelion. If that is true, we are seeing something never clearly observed before, either a natural fragmentation event that somehow launched pieces along long, clean, straight trajectories, or the controlled release of subcomponents from a larger parent body. This leads to a more practical question. If 3IATLAS did release many objects, where are they now? If they have been moving at about 500 meters per second for 22 days, they have already traveled about 1 million kilometers. By the time 3IATLAS reaches its closest point to Earth on December 19th, at a distance of about 269 million kilometers, those smaller bodies, if they exist, will have been moving for about 51 days. At the same speed, they would then be roughly 2.2 million kilometers from the main nucleus. That is still close enough, on a cosmic scale, for them to be linked to 3IATLAS, but far enough that good telescopes might pick them up as separate points of light. Loeb therefore calls for the strongest instruments we have to be pointed at 3IATLAS, the Hubble Space Telescope, the James Webb Space Telescope, and others capable of high-resolution imaging and spectroscopy. He wants direct measurements of the jet speeds, the rate of mass loss, and the composition of the outflow. Natural sublimation of cometary gas tends to stay below about 400 meters per second, roughly the sound speed in gas heated to a few hundred degrees. If the jets are found to move much faster, say 1 or 2 kilometers per second, that would point to more energetic processes. Chemical rockets can produce exhaust speeds of about 3 to 5 kilometers per second. Ion thrusters can reach 10 to 50 kilometers per second. Knowing the true velocity range would narrow down the options. Some astronomers resist this focus. They worry that spending limited telescope time to test an artificial origin will seem like supporting fringe ideas and feed online speculation. They point out that parts of the internet have already decided that 3IATLAS is an alien craft no matter what data come in. In that sense, their concern is understandable. The counterpoint is straightforward. If 3IATLAS is natural, then it may be the most unusual natural comet yet seen, and understanding it will improve our models of comet physics and interstellar bodies. If there is even a small chance that it is not natural, the cost of not checking carefully is very high. Letting an interstellar visitor pass through our solar system without using every reasonable tool to study it, simply out of fear of public reaction, would mean stepping away from the basic goal of science: to observe, to question, and to seek accurate answers. At the center of this discussion is one simple issue. If many objects really left 3IATLAS, are they just pieces of ice and rock, or are they probes of another kind? From there, it is natural to ask what follows if Avi Loeb is correct. If the sideways jets in the November 20th image are real, not just a satellite track, and if they are the trails of objects that left 3IATLAS near perihelion, what could those objects be? And how would we tell natural pieces from technological probes? The safest place to begin is with the natural picture. 3IATLAS is likely a loosely bound mix of ice and rock that has drifted through interstellar space for very long times, perhaps billions of years. Along the way, it has met cosmic rays, tiny impacts from dust grains, and changes in temperature when it passed near other stars. All of that tends to open cracks and weak layers inside. When such a body finally comes close to a star, the surface can jump to temperatures of hundreds of degrees. Thermal stress alone can split the nucleus. Add the force of gas blasting outward as buried ices turn to vapor, and you have conditions that often lead to breakup. We have seen this kind of thing before. Comet Shoemaker-Levy 9 broke into more than 20 pieces before those pieces fell into Jupiter in 1994. Comet Linear came apart as it moved toward the Sun in the year 2000. Comet Ison did not survive its close passage in 2013. Fragmentation is a normal part of comet behavior. In that sense, the fact that 3IATLAS has not obviously broken into pieces is more surprising than the idea that it might have lost some smaller chunks near perihelion. So if future data show that small bodies really did separate from the main nucleus, the first guess should be that they are natural fragments, blocks of ice and rock that cracked loose under heat and pressure. The details, however, are important. Once a fragment is on its own, it usually spins, outgasses in an uneven way, and develops its own little jets. Its path is then slightly pushed and pulled in complex ways. A group of fragments tends to spread into a wider and wider cloud of debris. The November 20th image, if taken at face value, does not show a broad cloud. It shows two narrow, straight lines reaching roughly perpendicular to the line between the comet and the Sunday. That kind of neat geometry is hard to get from purely random breakup. Supporters of a natural explanation reply that we might not be seeing the fragments themselves, only the dust they leave behind. The idea is similar to contrails from an airplane. The plane can twist and turn, but from far away, its long, thin plume can still look like a straight band. If fragments were thrown out along two tight jets, one in each direction, and each fragment shed dust as it warmed, the dust could sketch out straight lines even while the chunks themselves tumbled. That is a reasonable counterpoint, but it raises another question. Why would the breakup send material along paths that are perpendicular to the sun direction? In a typical breakup, pieces fly off in many directions, and the overall pattern is closer to a rough sphere than to a cross. To prefer two directions much more than the others, the nucleus would need a built-in weakness, like a crack or fault that failed in a special way. Having that crack lined up just right would be a coincidence, though not an impossible one. Loeb has estimated what is needed for natural fragments to match the observed X shape. If the mini-objects left near perihelion on October 29th and have reached about 1 million kilometers in 22 days, their average speed relative to 3IATLAS is around 500 meters per second. That is somewhat higher than a typical sublimation flow of about 400 meters per second, but still in the same general range. A sudden outburst from a pressurized pocket under the surface could in principle throw chunks that fast. Comets can trap very volatile ices beneath a tougher crust. When that crust cracks, gas can rush out and carry solid material with it at high speed. So the average speed alone does not force an artificial explanation. The time behavior is more worrying. If the mini-objects are merely ice blocks blasted outward, they should be evaporating as they move away. They should develop their own small comas and tails, break further under stress, and eventually smear into a general haze. After a few weeks, the neat lines should fade. If instead the jets stay narrow and straight for more than 20 days, that suggests that the sources have some internal strength and are not just loose piles of rubble. That is where the technological idea comes in. If the mini-objects are not simple fragments, one clear alternative is that they are probes, small craft, released from a larger vehicle to explore many places at once. This is not a strange thought in space engineering. Human space missions already use this model. Large spacecraft like Voyager and Cassini have carried smaller probes. Cassini released the Huygens probe to descend through the thick atmosphere of Titan. The Galileo orbiter carried an entry probe that dropped into Jupiter's atmosphere. Sending a main craft with one or more subprobes is a standard way to study several targets in a single mission. For a fast interstellar traveler, that logic becomes stronger. A body moving at about 60 kilometers per second with respect to the Sun cannot slow down easily. It will pass through the inner system on a single, brief track. To gather data on Mars, Earth, Venus, and perhaps Jupiter, a single fixed path is not enough, because the planets are spread out. One way to cover more ground is to release smaller vehicles that adjust their paths slightly towards specific goals, while the main craft stays on its original course and receives their reports. Seen in that light, 3IATLAS would be the carrier, and the sideways trails would mark the tracks of probes, keeping steady headings of their own. Because they use thrusters and attitude control, they would not share the main body's rotation. Their exhaust could produce straight, well-aligned streaks even while the parent object spins. Testing such ideas comes down to measurement. One clear test is speed. Natural comet jets, driven by sunlight turning ice to gas, tend to top out around 400 meters per second. Chemical rocket exhaust, in contrast, usually falls in the range of 3 to 5 kilometers per second, and ion thrusters can reach 10 to 50 kilometers per second. If careful spectra show that gas in the sideways jets is moving at several kilometers per second, that would be very hard to explain with normal sublimation. If the speeds match the lower, natural range, the case for technology becomes weaker. Another test is composition. Typical comet jets are mostly water vapor with carbon dioxide, carbon monoxide, and small amounts of other molecules. If the jets from the mini-objects show elements or compounds that do not fit a simple icy mixture, especially if they match known propellant types, that would be important. A third test is to look for the objects themselves as separate points of light. If they are compact and solid, Large telescopes should be able, at least in principle, to pick out a few of them. This is why the close approach on December 19th matters. At a distance of about 269 million kilometers, 3IATLAS will be close enough for the Hubble Space Telescope to resolve. Features a few hundred kilometers across, and for the James Webb Space Telescope to take spectra of the coma and jets with high quality. Large ground-based telescopes with adaptive optics may also separate any sizable mini-objects from the main glow, if they are present, and if observations are planned. Loeb has been arguing for just such a campaign. He wants Hubble, Webb, and major observatories on Earth to spend time following 3IATLAS during this window, measuring jet speeds, mass flow, composition, and searching the region near the nucleus for discrete objects. The difficulty he faces is not mostly technical. We already use these tools on comets. The difficulty is social. Many astronomers are uneasy about pointing top-level instruments at an object mainly to test an artificial origin idea. They worry that doing so will encourage a wave of similar claims about every odd asteroid or comet, burying serious work under a flood of speculation. Loeb's answer is that ignoring anomalies is more damaging than studying them. If 3IATLAS turns out to be a natural object, detailed observations will still improve our understanding of what interstellar comets can be like. If there is even a small chance that it is not natural, the risk of missing that fact is large. An interstellar probe moving through our system would have deep scientific and cultural importance. Choosing not to look closely because of fear of criticism would go against the basic aim of science, which is to check reality as carefully as we can. Thinking through the technological scenario also forces us to face the timescales involved. If 3IATLAS is a probe, it must have been launched long ago. Based on its speed and direction, Loeb estimates that it may have been traveling for billions of years. That would mean the builders could belong to a civilization that has already ended. Stars change. Planets can be sterilized by extreme events like supernova explosions or strong gamma-ray bursts. The galaxy is old, and the journeys of slow interstellar craft take a very long time. 3IATLAS could be a relic, like a message in a bottle from a culture that rose and fell before Earth formed. Another possibility is that its makers are still active somewhere in the galaxy and are waiting to see what their probe finds. If the small objects around 3IATLAS are probes, and if some of them are headed toward Earth, Mars, or Jupiter, they may eventually arrive at their targets and complete a survey. We do not know what they would then do. They might send a signal, destroy themselves to avoid contamination, or simply continue to record in silence. Meanwhile, people on Earth try to make sense of limited data. Some online communities have already decided that 3IATLAS is an alien vehicle. They point to the X pattern as evidence of engines, to the anti-tail as evidence of steering, and to NASA's careful wording in the November briefing as evidence of a cover-up. Even if those conclusions are not justified, their intensity reflects how unusual this comet already appears. It is worth noting that the clear X pattern in the November 20th image exists only because patient amateur observers took the time to collect and combine many long exposures. Michael Yeager, Gerald Raymond, and Enrico Prosperi are private astrophotographers, not staff at a national observatory. Their work revealed structure that had not been widely discussed. NASA's Mars-based image from October 2nd shows a similar pattern, but in the official press event, that feature was not a main focus. It appeared as one frame among many. There are simple reasons for that choice. Space agencies try not to highlight visual patterns before they understand them, because doing so can feed stories that are hard to correct later. They prefer to release data, let experts analyze it through peer review, and talk about firm results. That cautious method is part of how modern science maintains reliability. So, at this point, we are left with an interstellar object that shows 12 noted anomalies and a set of images that suggest organized structure in its outflow. Those structures could still turn out to be the result of unusual but natural physics, or they could point to deliberate design. For now, the only way to move from guesswork to knowledge is to keep watching 3IATLAS as closely as we can. From today to closest approach, there is about 1 month. That is a narrow window to make the measurements that could answer the basic question: is 3IATLAS simply a comet, or is it something we should treat as a much more serious case? To understand why this window feels so important, it helps to look at what happened earlier in the year. On October 1st, the United States federal government entered a shutdown when Congress does not pass a budget in time. Many agencies run out of legal authority to spend money. Non-essential staff are sent home without work. Projects pause. For an agency like NASA, one of the first things to slow down is public communication. The timing lined up almost exactly with key stages in 3IATLAS's path. October 1st was 3 days before its closest approach to Mars. It was about 4 weeks before perihelion. It was exactly when telescopes and spacecraft should have been watching most closely, while the object was near a planet and just about to be strongly heated by the Sunday. During this period, the Deep Space Network still operated, and spacecraft still followed pre-planned observing programs. The Mars orbiters took their images on October 2nd and 3rd, but the steady flow of updates, plots, and early analyses to the public almost stopped. When a normally open agency becomes quiet, people notice. In the absence of new information, guesses rush in to fill the gap. Some assume that data are being hidden. Others think nothing important is happening. For Avi Loeb, who had already argued for years that science treats anomalous objects too cautiously, the silence during this crucial month was especially frustrating. He spoke in interviews and posts about how the shutdown hit just when 3IATLAS might have been changing most quickly, passing Mars, approaching perihelion, and perhaps releasing material. The official account is simple. During a shutdown, many NASA employees are legally not allowed to work. They cannot process raw downlinks, run detailed models, write press releases, or answer questions from reporters. Spacecraft continue to run because their commands are prepared in advance, but the people who interpret their data and share conclusions with the public are not on duty. In that sense, the gap in communication was a side effect of a budget dispute, not a deliberate choice linked to 3IATLAS. Even if that is true, the timing still matters. When scientists are not at their consoles, they cannot request new observation sequences, adjust pointing, or coordinate across missions in real time. Opportunities pass by. The loss is not only in what was seen, but in what might have been seen with a quicker response. We can trace this in the records. On October 2nd, the Mars Reconnaissance Orbiter turned its high-resolution imaging science experiment, or HiRISE, camera toward 3IATLAS from about 19 million miles away, roughly 30 million kilometers. HiRISE can see details as small as about 30 centimeters on the surface of Mars. At comet distance, it could not resolve such fine scales, but it should still see structures on the order of a few tens of kilometers. The HiRISE image of 3IATLAS did show structure, including an X-shaped pattern in the material around the nucleus, with 4 preferred directions of outflow, where simple models expect only 1 or 2. However, this image was not made public until November 19th, about 48 days later. When it was finally shown, it appeared as one frame among many in a longer briefing, not as a main result. NASA's explanation is again tied to the shutdown. The spacecraft sent the data back through the Deep Space Network, but there were not enough staff on duty to fully process, interpret, and label the images for release. Loeb argues that the delay had a cost. If the X pattern had been shared in early October, he believes there might have been time to plan follow-up observations, to repoint other spacecraft, and to request time on telescopes like Hubble and James Webb, while 3IATLAS was still near Mars and relatively bright. By the time the image was released, perihelion was already past, and the object was heading outward, slowly fading. Another Mars-orbiting spacecraft, the Mars Atmosphere and Volatile Evolution Mission, or MAVEN, also observed 3IATLAS. MAVEN normally studies the upper atmosphere of Mars and the way the solar wind removes gas. Its sensors are tuned to detect hydrogen, oxygen, carbon, and related ions. When the comet passed near Mars, those same instruments could see the giant hydrogen cloud around 3IATLAS, which traces the breakdown of water molecules. On October 9th, MAVEN measured a hydrogen coma about 200,000 kilometers across, larger than the distance from Earth to the Moon. That implies very strong water production. This result, too, was shared only in November. It leads to further questions. MAVEN carries particle detectors that can measure the speeds and types of ions in the solar wind. If 3IATLAS released anything unusual, charged particles or plasma not matching standard comet outgassing, MAVEN could, in principle, have seen it. So far, detailed results from the days just around perihelion have either not been released or are still in analysis. The European Space Agency, by contrast, was not affected by the United States shutdown. Its missions Mars Express and the ExoMars Trace Gas Orbiter continued operations as usual. The Trace Gas Orbiter imaged 3IATLAS on October 3rd from about 32 million kilometers away. ESA released these images quickly. On October 7th, they showed the comet as a small, slightly fuzzy point of light, without the fine structure that HiRISE can reach, but still useful for tracking its position. ESA used the exact positions measured in those images to refine the orbit of 3IATLAS. When they compared the observed positions to those predicted by a gravity-only model, they found small but real differences, on the order of a few thousand kilometers. The comet was being gently pushed off its expected path. The most straightforward explanation was non-gravitational acceleration from outgassing, the same basic effect that Loeb later discussed. ESA published this analysis on October 22nd, describing the extra acceleration and using it to improve future position predictions. During this same period, NASA did not publish comparable updates on 3IATLAS. The combination of ESA's activity and NASA's silence added to public uncertainty. Online discussions about the comet became more speculative. In some forums, people claimed that 3IATLAS had changed course toward Earth, that it was accelerating in unnatural ways, or even that radio signals had been detected and hidden. None of these claims were supported by data, but without frequent, clear, official updates, they spread widely. On November 7th, soon after the shutdown ended but before NASA's large November 19th briefing, Loeb appeared on a long-form podcast and talked about 3IATLAS for over an hour. He described the list of anomalies, raised the possibility of a technological origin, and criticized the delay in releasing spacecraft images. He also said that a scientific journal had resisted publishing his paper unless he removed a sentence suggesting that the object's path might have been designed. According to his account, editors felt that this sentence went beyond acceptable scientific hypothesis into speculation that could be read as sensational. Loeb chose to keep the line and instead posted the paper on an open preprint server where other researchers can read it, but it does not carry the weight of peer-reviewed publication. For him, this experience fits a broader pattern. He sees a field that is reluctant to entertain unusual possibilities, even when standard models are under strain. Many astronomers disagree with his interpretation of the data and think that each of the 12 anomalies can be explained within natural comet physics, especially if we accept that interstellar objects may be more varied than we expected. They argue that invoking technology is not necessary and is not yet supported. At the same time, it is hard to deny that the shutdown removed some opportunities. For 41 days, 3IATLAS was near its brightest and most active. Those were the very days when rapid response observations would have been most informative, and when staff limitations were also strongest. The comet passed perihelion on October 29th. Since then, it has been moving away from the Sun, and its overall activity is expected to decline. By the time it reaches closest approach to Earth on December 19th, the jets should be weaker and the coma smaller. We will still be able to study it, but the best moment to see the most dramatic behavior is already behind us. Was the shutdown arranged to hide 3IATLAS? Almost certainly not. The budget dispute that caused it was about domestic policy, not astronomy. The overlap with the comet's most interesting weeks appears to be an accident, though an unfortunate one for science. Yet from the outside, coincidence can look like intention when explanations are slow and incomplete. The longer an information gap remains, the more some people come to see it as a sign of control rather than simple delay. There are still many open questions. Maven's particle instruments surely gathered large amounts of data while 3IATLAS was nearby. Detailed results from that period, especially around perihelion, have not all been presented yet. Mars rovers such as Perseverance and Curiosity carry cameras that can look at the sky as well as the ground. It is natural to ask whether any of them were pointed toward the comet, and if so, what they recorded. Solar observatories like the Solar and Heliospheric Observatory, or SOHO, monitor the region around the Sun almost continuously. 3IATLAS passed through their fields of view between about October 15th and 26th. There should be image sequences from that time. Some of these products have been shared, others are likely still in internal pipelines. Some may never be fully processed simply because there is more data than people to handle it. In that sense, NASA may not be hiding anything at all. It may instead be working under real limits of staff and time, sorting through measurements from about 15 spacecraft that all observed the same object, turning raw voltages and pixel counts into trustworthy, calibrated science takes care. It cannot be rushed without risking mistakes. But whatever the internal reasons, the public result looks like a gap, a period when an unusual interstellar visitor was active and the official story advanced only slowly. And that gap has consequences. One of those consequences is how we now look at the anti-tail of 3IATLAS. Among all its strange behaviors, this is the one that troubles many physicists the most. Anti-tails in normal comets are supposed to be tricks of perspective. When you correct for viewing angle and orbital geometry, they turn back into ordinary dust trails. With 3IATLAS, that does not seem to happen. Its anti-tail looks like a real structure, material flowing roughly sunward against the general push of the solar wind. To understand why that is odd, it helps to review how comet tails usually form. As a comet approaches the sun, sunlight heats the surface. Ices of water, carbon dioxide, and carbon monoxide turn directly from solid to gas. The gas escapes into space, dragging dust off the surface. The solar wind, a stream of charged particles flowing outward from the sun at speeds of about 400 to 800 kilometers per second, pushes the gas away from the Sunday. Small dust grains only a few micrometers across also feel strong pressure from sunlight and form the classic thin tail pointing away from the Sunday. Larger dust grains, tens to hundreds of micrometers in size, are much more massive and harder to push. They tend to stay close to the comet's orbit, forming a broader, curved trail that follows the path of the nucleus. From Earth, we see only a two-dimensional projection of this three-dimensional structure. If the comet's orbit is tilted relative to our line of sight, the curved dust trail can sometimes appear to point toward the Sunday. That apparent forward-pointing structure is a normal antitail. The dust is not really moving sunward. It is simply following the orbit, and geometry makes it look reversed. For more than a century, astronomers have been able to explain antitails in this way. Once you include the right viewing geometry, the illusion disappears. With 3IATLAS, several groups, including Avi Loeb and his collaborators, have done the geometry and still find a persistent feature aligned roughly toward the Sunday. The conclusion is that there is a genuine sunward component in the outflow that needs explaining. The simplest natural idea is that 3IATLAS is throwing out unusually large dust grains. Loeb estimates that to sustain the observed antitail, the dust grains would need to have an effective radius of about 100 micrometers, roughly the size of fine sand. A grain like that is around 1 million times more massive than the tiny dust particles often used in standard models. Large grains have much more inertia. When the solar wind and radiation pressure push on them, their motion is not changed as easily. If the grains are launched roughly toward the sun, they will keep going that way until the pressure of the solar wind slowly brings them to a stop. Calculations suggest that for grains of that size and speed, the balance point lies about 1 million kilometers from the nucleus. That is also the scale at which the antitail appears to fade in images, such as the November 9th image by Frank Neblung and Michael Buchner, where the sunward feature extends to roughly 1 million kilometers and then becomes too faint to see. So far, this fits the large grain model. The next difficulty is how to launch such large grains at high speed in the first place. Typical comet outgassing accelerates small particles to a few hundred meters per second. That is enough to lift them off the surface, but not enough to casually throw sand-sized grains to speeds around 500 meters per second. To do that, you need strong pressure, such as from volatile gases trapped under a crust that suddenly cracks. Comets are known to have short outbursts like this. What is unusual in 3IATLAS is not the idea of an outburst, but the duration and focus of the activity. Observations suggest that a sunward jet has been present since about July, roughly 5 months of continuous or nearly continuous activity in one preferred direction. Loeb's estimates indicate that to maintain such a feature with large grains, the comet would have to lose mass at a rate of about 50 billion tons per month. That is on the order of 1% of its estimated total mass every month. At that rate, the nucleus would be used up in only a few years. This leads to a fork in the natural explanation. Either the true mass loss rate is lower than that estimate, which would mean that the antitail must be created by a different mechanism than simple large dust grains, or the rate is accurate, and 3IATLAS is in the middle of a slow, organized disintegration. Neither option settles comfortably into the picture of a quiet, ordinary comet. Because of that, Some researchers have considered another possibility. Perhaps the antitail is not dominated by dust at all, but by gas in the form of plasma, meaning ionized gas that carries electric charge. Charged particles do not just feel the push of the solar wind. They also follow magnetic field lines. The sun's magnetic field is complex, with loops and arcs that extend far into space. If 3IATLAS is releasing ionized material, that plasma could be guided along those magnetic structures. Depending on how the field is shaped locally, some paths might bend back toward the sun, creating a roughly sunward jet. However, for this to work, 3IATLAS would need an unusually strong electrical interaction with its environment. Most comets release neutral gas that becomes ionized only farther out, after exposure to solar ultraviolet light. To make a magnetic channeling model effective, the gas would need to be ionized more quickly or more completely, or the comet would need some mechanism near the surface that generates electric currents. At this point, the discussion becomes more speculative. If the comet is interacting with the solar magnetic field in a special way, that may reflect a rare composition, a particular internal structure, or some combination of both. Natural objects can carry stored energy in volatile ices and release it over time. Radioactive decay can supply low-level internal heat. Layered arrangements of different ices can produce multiple stages of outgassing as new layers are exposed. It is possible to imagine 3IATLAS as a finely stratified body where each new layer drives a different pattern of jets. All of these ideas stay within the realm of natural physics, but they require a very organized interior. The nucleus would need to have formed in a way that produced distinct layers and fault lines, with certain cracks lined up to give long-lived jets. The more such fine structure we assume, the more the comet begins to look like an object with a carefully arranged design, rather than a random clump of ice and dust assembled in a protoplanetary disk long ago. A November 15th image by Tirasak Talawang shows not just a single antitail, but three main structures, one prominent sunward feature, and two more tails pointing roughly away from the sun, but at different angles. Multi-tail comets are not unheard of. Hale-Bopp, for example, showed both a dust tail and a gas tail, both pointing generally away from the sun, but separated because dust and ions react differently to radiation pressure and magnetic fields. In the case of 3IATLAS, the key difference is that one of the strong features points toward the Sunday. That is the part that standard models struggle with. In the end, the choices keep returning to a simple split. Either 3IATLAS is showing us an extreme example of processes that natural comets can produce but almost never do, which would make it the most unusual natural comet yet studied, or it is doing something that natural comets, as we currently understand them, should not be able to do, which would mean we are dealing with a different category of object. There is not much safe middle ground. Unusual features in isolation are easy to dismiss. Unusual features are fine. Anomalies happen. When you put one anomaly on top of another, when every new observation adds something that does not fit the standard picture, it becomes fair to ask whether the picture itself is wrong, or whether the object simply is not what you thought it was. The antitail is only one part of that story, but it is a part that refuses to sit neatly anywhere. Every attempt to force it into place makes the overall puzzle more complicated. The same is true for the mass loss estimates. Loeb's figure of about 50 billion tons of material per month sounds extreme. On first hearing, it sounds like a comet destroying itself. To know if that is realistic or not, you have to compare it with the total mass of 3IATLAS, and with what other comets lose. The total mass is not well known. Hubble Space Telescope observations from August suggest that the nucleus diameter could be as small as about 440 meters or as large as roughly 5.6 kilometers. That is a wide range. If the diameter is about 440 meters, and if the average density is around 500 kilograms per cubic meter, the mass would be on the order of 20 billion tons. If the diameter is 5.6 kilometers, the mass could be near 50 trillion tons. Hubble cannot see the solid core directly. It measures the brightness of the coma and works backward, which leaves a lot of room for error. Loeb tried a different approach. He looked at the lack of measurable non-gravitational acceleration before October. Active comets that outgas strongly feel small thrusts from their jets, and those thrusts bend their orbit slightly. By demanding that the observed path stayed close to a gravity-only orbit during the months before perihelion, he estimated a minimum mass, about 33 billion tons. If the comet were lighter than that, the early outgassing should already have left a detectable imprint. So 33 billion tons is a lower limit. The real mass could be much higher. Now compare that to 50 billion tons per month. If the nucleus really were only 33 billion tons, then a continuous loss of 50 billion tons a month would destroy it in less than 1 month, which clearly has not happened. That tells us that at least one of the inputs is wrong or incomplete. Either the true mass is larger than the lower limit, or the 50 billion tons per month only applies during a short, intense phase, or the assumed outflow speed is off, or some combination of all three. The mass loss estimate is built from the length and brightness of the jets, especially the antitail. The antitail stretches about 1 million kilometers. Using how it appears to interact with the solar wind, Loeb and others can estimate the density of particles out near that distance. Even if the local density is only a few proton masses per cubic centimeter, when you multiply that by the huge volume of a structure, 1 million kilometers long and hundreds of thousands of kilometers wide, the total mass adds up quickly. Outflow speed is the key factor. If the material is moving at around 400 meters per second, a typical speed for gas blown off by sunlight from ice, then the amount of mass needed to fill that volume and maintain that brightness leads to a loss rate on the order of 50 billion tons per month. But if the speed is higher, the required mass drops. The rate scales roughly in inverse proportion to the velocity. If the jets are actually moving at 2 kilometers per second instead of 400 meters per second, the mass loss estimate shrinks by a factor of 5, down to about 10 billion tons per month. To know which case is real, we need the true jet speed. That requires high-resolution spectroscopy that can resolve Doppler shifts in the emission lines of gas in the jets. Telescopes like Hubble and James Webb can do that, but only if they are pointed and scheduled. So far, that kind of data is limited or still being processed, which means that numbers like 50 billion tons per month still carry large uncertainties. There is another twist here. If the outflow speed turns out to be only a few hundred meters per second, the mass loss rate is high, but still just barely within what solar heating alone might support. If the outflow speed is several kilometers per second, the mass loss rate becomes easier to sustain in terms of how much mass is lost, but much harder to explain in terms of energy. Velocities of a few kilometers per second are common in rocket exhaust. They are not expected from simple sunlight on ice. In that sense, the very measurement that saves the mass budget could challenge the assumption of purely natural jets. For the moment, suppose the natural case holds. and the speed really is around 400 meters per second, then the question becomes, how long can 3IATLAS keep losing mass at this rate? If the nucleus mass is only tens of billions of tons, a sustained loss of 50 billion tons per month would erase it quickly. The most reasonable way to soften this is to accept that the loss rate is not constant. Comets often go through bursts of activity. They brighten, then calm down, then brighten again. The high rate near perihelion might last only for a short time. If, for example, 3IATLAS lost perhaps 1 billion tons per month from July through most of October, then around 50 billion tons per month during a brief peak near perihelion and early November, and then fell back to around 1 billion tons per month afterwards, the total loss across its passage through the inner solar system might add up to only 10 or 20 billion tons. That is still a lot, but a large nucleus could survive it. This patch raises another puzzle. Why did the comet stay relatively modest in activity on the way in, and then suddenly become extremely active near perihelion in a way that does not follow a smooth curve? In many comets, activity increases roughly as the square of the inverse distance to the Sun, tracking the growing solar energy. In 3IATLAS, observations suggest step-like changes and new jets appearing after perihelion that were not seen before. One way to explain this is partial fragmentation. If the nucleus cracked near perihelion into several sizable pieces that remain close together and still gravitationally bound, each piece could start outgassing on its own. The combined effect could be a sudden jump in activity and a more complex jet pattern, without any single fragment being especially exotic. The complication is that current images, such as those from November 11th by David Jewett and Jane Liu, still show what looks like a single nucleus, not a chain of fragments. Any pieces must either be too small to resolve or still crowded so close together that they blur into one point. If the breakup were recent, it might take weeks for the fragments to spread far enough apart to be visible as separate points of light. By the time of closest approach on December 19th, if fragmentation has occurred, high-resolution telescopes like Hubble should start to see signs of multiple bodies. If no such signs appear, then large-scale fragmentation is probably not the main driver. That brings everything back to the energy balance. Solar power at 3IATLAS's distance at perihelion can be estimated. For a nucleus on the order of 5 kilometers in diameter, the total solar power intercepted is on the order of a few tens of gigawatts, roughly comparable to a few dozen large power plants. Only a fraction of that power can go into lifting and accelerating material. Much of it is reflected or re-radiated as heat. If only 10 to 20% is available for driving outgassing, that leaves perhaps a few gigawatts of useful power. The energy needed to lift tens of billions of tons of material per month and accelerate it to hundreds of meters per second is large but not impossible for that power input. A rough calculation shows that the kinetic energy of 50 billion tons moving at about 400 meters per second is on the order of 4 times 10 to the power of 18 joules. Spread over a month, that corresponds to an average power of a little more than 1 gigawatt. That fits within the few gigawatts available from solar heating in this simple estimate. The margin, however, is not huge. If the true mass loss rate is higher, or if the outflow speed is significantly faster, then sunlight alone may not be enough. If solar heating cannot fully account for what we see, we have to think about other natural sources of energy. Internal heat from radioactive decay is far too weak in a small body like this. Tidal heating needs strong gravitational interactions with a nearby large planet, which 3IATLAS does not have. Chemical energy from unstable compounds is possible in principle, but most materials that could release that much energy would not survive intact over billions of years in interstellar space. That leaves, in the natural category, stored energy in extremely volatile ices. Substances like nitrogen or methane can stay frozen and stable at the very low temperatures of interstellar space, around a few Kelvin. As a comet approaches a star and surface temperatures rise above about 60 or 70 Kelvin, these ices can begin to sublimate rapidly. If they lie beneath layers of more common ices like water and carbon dioxide, pressure can build until the overlying layers crack. The release can be explosive, carrying large amounts of material out in a short time. This mechanism is plausible and has analogues in the outer solar system. Bodies like Triton, Neptune's large moon, and Pluto show nitrogen ice and possible geyser activity. For 3IATLAS, such a model would require that it formed in a region rich in supervolatiles and kept a layered internal structure for a very long time. The timing would also need to line up so that the most volatile layers were exposed just as it passed perihelion. So, for each anomaly mass, activity pattern, jets, anti-tail, energy, we can describe a natural scenario. None of these scenarios is impossible. They all draw on known physics, but taken together, they ask 3IATLAS to be unusual in many different, specific ways at the same time. At that point, it is reasonable to ask whether we are looking at one extreme outlier in a large population, or whether our idea of what is normal for interstellar objects is incomplete. Maybe the galaxy is full of active, complex comets like this, and our local sample has simply been too small and too biased to show it. Or maybe 3IATLAS really is special, shaped by a unique history or by something else entirely. And while we ask those questions, there is one more factor in the background: the long pauses and limited answers from some of the very institutions that hold the most data about this object, the radio silence that speaks volumes. One natural question now is what we should expect if 3IATLAS is not natural at all. If it is a probe, a carrier, or any kind of technological craft, most of us would expect it to emit something: radio waves, laser pulses, some form of signal. That is what spacecraft do. They gather data and send it somewhere. If we could detect even a tiny piece of such a transmission, the debate would end very quickly. A confirmed artificial signal would tell us, without ambiguity, that 3IATLAS is not just a comet. This is not a wild leap. Every spacecraft humans have launched uses radio. Voyager 1 and Voyager 2, now more than 20 billion kilometers from Earth, still send back data with transmitters of roughly 23 watts. Less power than a small light bulb, yet our radio telescopes can still hear them. If 3IATLAS carries any transmitter at all, even one as weak as a mobile phone at a fraction of a watt, it should be detectable when the object is only a few 100 million kilometers away. Because of this, researchers in the search for extraterrestrial intelligence have already pointed their instruments at 3IATLAS. SETI projects usually focus on faraway stars, hoping to catch a beacon or accidental leakage from distant civilizations. Here, instead, they have a nearby moving target that could, in principle, be artificial and is currently inside our solar system. On November 5th, the Meerkat radio array in South Africa observed 3IATLAS. Meerkat uses 64 dishes, each about 13.5 meters across, working together as an interferometer. For this observation, it listened from about 900 megahertz to about 1,670 megahertz. a band where a lot of human radioactivity occurs. Mobile phones, some Wi-Fi, parts of global navigation systems, and other services. If 3IATLAS was using a radio system similar to ours in that band, Meerkat would have a good chance of noticing. During several hours of observing, the back-end system designed to search for techno-signatures flagged roughly 23,600 signals. On the surface, that number sounds dramatic. In practice, almost all such events are interference. The analysis showed that every one of those signals came from human sources: satellites, ground transmitters, radar, and other familiar emitters that happened to lie in the telescope's view. To separate real candidates from noise, the software checks whether a signal moves across the spectrum exactly as a source at the comet's position should. 3IATLAS is moving relative to Earth and the background stars, so a true signal from it would show a Doppler drift and would remain tied to the comet's sky position as the telescope tracks. Interference from Earth or near Earth does not behave that way. None of the signals followed the expected pattern. The result was a non-detection. From this, scientists can set a limit. At the distance of about 334 million kilometers on that date, any transmitter on 3IATLAS radiating in that band with a power above about 0.17 watts would probably have been found. That is roughly the output of a low-power handheld device. So, 3IATLAS is not emitting strong, steady radio in that frequency range. That does not prove it is quiet at all frequencies. It simply rules out human-like radio transmission in that part of the spectrum. The electromagnetic spectrum is huge, spanning more than 20 orders of magnitude in frequency, from very low-frequency radio to gamma rays. Meerkat's search covered a narrow slice. Saying that it saw nothing is like sampling one small bucket of ocean water and finding no fish. It tells you something useful about that specific bucket, but not about the entire sea. There is also a good reason to think that very advanced systems might not use radio for long-distance communication. Radio waves spread, power falls off with the square of distance. Lasers can form very tight beams and deliver information with far less energy loss. We are already planning laser links for our own deep space probes. For an interstellar craft, laser communication to a distant home system would be more efficient than radio. However, that efficiency comes with a catch. A narrow laser beam is only visible to observers who lie almost exactly along its path. If 3IATLAS is sending a laser signal to some other star, the thin beam might pass millions of kilometers from Earth, and we would never know. Instead of looking only for deliberate transmissions, we can also look for waste heat. Any machine that uses energy must dump some of it as heat. That heat radiates in the infrared. A craft with a significant internal power source should show an infrared signature that is warmer or more structured than a simple sun-heated ice ball. The James Webb Space Telescope is very sensitive to infrared light. On August 6th, Webb used its near-infrared spectrograph to study the gases around 3IATLAS. The spectrum showed carbon dioxide, water, carbon monoxide, and carbonyl sulfide, all standard cometary components. The thermal behavior appeared consistent with a cold, icy nucleus warmed by sunlight. There was no obvious sign of extra internal heating in the data released from that date. Those results are reassuring if you favor a natural explanation, but they are not the final word. August 6th was almost 3 months before perihelion. The comet was cooler and less active. If there is any internal system that only turns on under high stress or at particular stages of the orbit, it may not have been operating then. What we really need are infrared observations from around late October and early November, when 3IATLAS was at its most intense and showing the complex jets and anti-tail. If such data exist, they are not yet widely public. This pattern repeats. When we look, we see nothing obviously artificial, but our coverage is incomplete in both time and frequency. The lack of a clear signal matches what we expect from an ordinary comet. It also matches what we would expect from a cautious probe designed to avoid detection, perhaps by storing data on board and transmitting only when safely far away from any potentially curious civilization. Because non-detection can be explained either way, Avi Loeb has suggested a way to think about these cases more systematically. He uses a Loeb scale from 0 to 10 to rate interstellar objects. A score of 0 means definitely natural. A score of 10 would mean definitely artificial and likely of concern. 3IATLAS, in his view, currently sits at about 4. That reflects multiple unexplained anomalies, but no decisive proof of technology. To move up that scale, we would need direct technosignatures, a confirmed artificial signal, a strong infrared excess that cannot be explained by sunlight, a spectral line that points to manufactured material or dynamical behavior that natural physics cannot reproduce. The sideways jets and the possible release of many small objects are especially important here. If we can show that several bodies really did leave the nucleus near perihelion and are following paths and speeds that loose ice fragments could not maintain, that would count as strong evidence. Getting that evidence requires more observations while 3IATLAS is still within reach. High-resolution imaging from Hubble and other large telescopes could look for individual mini-objects near the main body. Detailed spectroscopy could measure jet speeds and compositions. Instruments near Earth might even detect a few molecules from the comet's outflow, if any drift into our local environment. All of this makes the next month important. By early next year, 3IATLAS will be farther away, fainter, and harder to study. December 19th, 2025 stands out as a key date. On that day, the comet will reach its closest approach to Earth at a distance of about 269 million kilometers, roughly 1.8 astronomical units. That is not close compared with some near-Earth asteroids or long-period comets that sweep much nearer. But 3IATLAS is not a typical visitor. It is an interstellar object, only the third such body we have ever confirmed. Distance affects everything we can measure. As an object moves away, its apparent brightness drops with the square of the distance. If the distance reduces by about 20% between late November and December 19th, the brightness increases by roughly 44%. For many instruments, that change is the difference between barely usable data and clean, detailed signal. Along with brightness, another factor matters just as much. Angular size also matters. Angular size is how large an object appears on the sky. It depends on both its true size and its distance. As 3IATLAS comes a little closer, its apparent size grows slightly. If there are fine details in the coma or jets, or if small objects are clustered near the nucleus, that change in angular size can make the difference between blur and barely resolvable. Hubble's sharpness is limited by diffraction, the wave nature of light. At a distance of about 300 million kilometers, Hubble can separate features roughly 300 kilometers across. At about 269 million kilometers, that limit improves to around 250 kilometers. That is still too coarse to see individual mini-objects a few kilometers wide, but it is enough to show patterns, clumps rather than a smooth glow, hints of repeated structure rather than a single uniform ball of fuzz. Spectroscopy adds another layer. By spreading the light into a spectrum and examining the positions, widths, and strengths of spectral lines, we can infer composition, temperature, and motion. The more photons we collect, the more precise these measurements become. At closest approach, 3IATLAS will give our instruments their best chance to gather those photons. James Webb, with its large mirror and high sensitivity in the infrared, is especially well suited for this job. High-resolution spectra of the jets could tell us not just which molecules are present, but also how fast they move toward or away from us via Doppler shifts. The widths of the lines can give rough temperatures. The strengths of the lines can suggest how dense the gas is in different regions. From that, clear tests follow. If the gas speeds are on the order of a few hundred meters per second and the temperatures match what we expect from sunlight on icy material at that distance, the jets fit a natural pattern. If speeds are several kilometers per second, or if temperatures are significantly higher than simple heating can explain, then we have to look for more energetic mechanisms. If the spectrum shows familiar cometary volatiles like water, carbon dioxide, and carbon monoxide, the case for a natural origin remains strong. If it shows unexpected metals or complex compounds that do not belong in a loose ice rock mix, we would have something harder to explain. Loeb has been very open about what he thinks should happen next. He has written, spoken, and repeated a simple line. This is a rare opportunity, and the best instruments we have should be used while the object is still relatively close. After December, 3IATLAS will head outward. It will pass near Jupiter in March 2026, and then continue into deep space at roughly 60 kilometers per second, fading beyond the reach of even our most powerful telescopes. The push to observe faces real obstacles. Time on Hubble and Webb is limited. Many research teams compete, and their proposals are judged carefully. Committees have to balance long-term surveys, deep looks at distant galaxies, studies of planets and stars, and everything else astronomers want to do. Against that backdrop, using a significant block of time to test the possibility that 3IATLAS is artificial can look like a risk. If most experts expect the object to be natural, then some reviewers may see such a program as low probability, even if the potential payoff is enormous. Loeb argues that, in cases like this, the usual cost-benefit thinking should bend. Even if there is only a small chance that the object is artificial, the implications of missing that fact are huge. If we choose not to look closely enough at an interstellar visitor, and it later turns out that we could have seen clear signs of technology, that choice would mark a major missed opportunity for science. He often points back to Oumuamua, the first known interstellar object, discovered in October 2017. It was noticed late in its passage, studied with the instruments available, and then it slipped away. We did not obtain clear images of its shape. We did not get the kind of detailed spectra that would settle debates about its composition. What we did get was enough to show that it behaved strangely, no visible coma, but a small, non-gravitational acceleration, and not enough to explain why. Years later, the literature on Oumuamua is still divided among competing natural models and, in Loeb's work, a technological one. There is broad agreement on one point. We needed better data, and we did not have it. 3IATLAS offers a second chance of a kind. It was discovered earlier. Multiple spacecraft have already observed it. Ground-based and space-based telescopes have followed it for months. In that sense, we are in a stronger position than we were with Oumuamua. Yet, the same pattern threatens to repeat. Cautious allocation of resources, concern about reputations, and a tendency to wait for definitive proof before acting boldly. So what might December 19th actually bring? If enough observing time is granted, if 3IATLAS behaves as a natural though unusual comet, then spectra from Hubble, Webb, and large ground-based telescopes should show ordinary comet gases at speeds and temperatures consistent with sublimation. Images should show a bright, somewhat asymmetric coma, perhaps with multiple jets and tails, but no small bodies cleanly detached from the main nucleus. Mass loss rates may be high. The anti-tail may remain puzzling, but everything would stay within a stretched version of known comet physics. If the object is artificial, observations could reveal discrete mini-objects moving on straight, steady paths that do not fit the messy motions of loose fragments. Jet speeds might be too high for passive outgassing. Infrared data could imply internal heat beyond sunlight. Geometric patterns might appear in the outflow that are hard to reconcile with random cracks and vents. In the best case, some instrument might catch a signal, whether radio or optical, linked in time and direction to the object. A third outcome sits between these two. Data might show new irregularities, new features that can be made to fit natural models only by adding more layers of special assumptions, and that also fit technological models only by leaning on our imagination. In that case, the arguments would continue. Different groups would publish different interpretations. The public would hear conflicting messages. Some would see evidence of something extraordinary. Others would see a complex, but still natural comet. In that environment, trust in scientific institutions can erode, especially if people feel that information is being delayed or softened. That is why the coming observations carry weight beyond pure data. They will test not just models of jet dynamics and mass loss, but also our systems for sharing uncertain knowledge. The way results are presented, how quickly, how clearly, and how honestly about what is known and unknown will shape how people think about 3IATLAS for years. If, in the end, the evidence points strongly toward an artificial origin, the change would be deep rather than sudden. There would be no automatic shift in daily life on the day a paper crosses the threshold from possible to probable. But over time, knowing that another intelligence once sent a device through our solar system would alter how we see our place in the galaxy, it would raise new questions about communication, exploration, and responsibility. If the evidence instead supports a purely natural but highly unusual comet, that too would matter. It would show that interstellar space can produce objects more active and varied than the comets we are used to. It would push us to revise our models of how icy bodies form and evolve around other stars. It would be a reminder that normal in astronomy often means what we have seen so far, not what is truly typical. Loeb does not expect a dramatic announcement on December 19th. He has said that the culture of science rewards caution. Any scientist who publicly claims that an interstellar object might be engineered faces a very high burden of proof. The standard response will likely remain that 3IATLAS is a comet, that the anomalies can be handled with more detailed models, and that more study is needed. At the same time, he points out that the raw measurements, the spectra, the images, the timing, the brightness curves, do not belong to any one narrative. Once they are released, other teams can analyze them independently. If jet speeds are indeed in the kilometer per second range, if the coma resolves into separate coherent bodies, if temperatures are higher than sunlight allows, those facts will be visible in the numbers themselves. Careful work can be slow, but it is hard to hide forever. In that sense, what matters most in the long run is not a single press conference or a single statement, but the patient accumulation of well-measured quantities, velocities, temperatures, compositions, positions. From those, step by step, a more solid picture of 3IATLAS will emerge. Whether that picture matches a stretched version of comet or requires a new category entirely is the question waiting on the other side of the data. In the end, the only honest path is to keep looking at the evidence, follow where it leads, and accept the answer even if it is not the one we expect. The universe is often stranger and more complex than our first models allow. Just as astronomers were trying to make sense of 3IATLAS, another object appeared. On November 2nd, Gennady Borisov, the same observer who discovered 2I Borisov, the second confirmed interstellar object in 2019, found a new body in the inner solar system. Its temporary name is C/2025 V1. People quickly started calling it V1. Its arrival has added a new layer to the story. The basic facts are these. V1 follows an orbit that is tilted by about 113 degrees relative to the plane of the planets. In other words, it is diving through the solar system on a path that is almost perpendicular to the ecliptic. That is unusual, but it is not unheard of. Long-period comets from the Oort cloud, the distant spherical shell of icy bodies around the Sun, often come in on paths with high inclinations. What caught attention was V1's orbital eccentricity. Early solutions gave a value near 1.95, with a large uncertainty of about plus or minus 0.26. An eccentricity greater than 1 means a hyperbolic orbit. The object is not bound to the Sun and will pass through only once, like 3IATLAS. But because the error bar is large, the true eccentricity could also be slightly less than 1. If it is, for example, 0.997 or 0.998, then V1 is actually on a very stretched but still closed orbit. In that case, it would come from the Oort cloud rather than interstellar space. To decide between those options, you can integrate the orbit backward in time, out to a distance where the pull of the planets is small compared with the Sunday. Around 1,000 astronomical units is a common choice. If, at that distance in the past, the eccentricity is below 1, the object likely belongs to the Oort cloud. If it stays above 1, an interstellar origin is more likely. When Loeb and others did this exercise, they found that at about 1,000 astronomical units, the eccentricity drops below 1. That suggests V1 is probably a long-period comet from our own cloud, rather than a true interstellar visitor. If V1 is just another Oort cloud comet, why does it matter here? Mainly because of timing and geometry. It was discovered only days after 3IATLAS passed perihelion. Its path, while tilted very differently, comes relatively close in space to where 3IATLAS was in October. The minimum distance between the two orbits is about 75 million kilometers. In everyday terms, that sounds huge, but on the scale of the solar system, where separations of billions of kilometers are normal, it is not so large. That closeness raises a natural question. Could V1 somehow be related to 3IATLAS? Could it be a piece that broke off? Or one of the hypothesized mini-objects that left near perihelion and then followed its own path? When you work through the numbers with gravity alone, the answer seems to be no. The measured non-gravitational acceleration of 3IATLAS is too small to fling a fragment onto V1's current orbit. The two bodies never come closer than about 225 million kilometers under simple dynamics. To bridge that gap, any fragment would need some form of additional push after separation. If V1 really did start from 3IATLAS and then adjust its course enough to reach its present trajectory, that extra push would need to act like propulsion. That would be a technosignature, evidence that the object is not just coasting, but steering. However, early images of V1 show it as a point of light with no clear coma or tail. For a body at its distance from the Sun and brightness level, that is a bit surprising. Many comets at similar distances show at least a faint haze of gas and dust. The absence of a visible tail does not prove that V1 is artificial. Some objects on comet-like orbits are in fact rocky asteroids that do not outgas because they contain little or no ice. If V1 is an asteroid, though, and its orbit really traces back to the Oort cloud, that would be odd. The Oort cloud is thought to be mainly icy. Rocky bodies are not expected to form or remain there in large numbers. Right now, astronomers consider several possibilities. One is that V1 is a dormant comet from the Oort cloud, built mostly of ice, but currently inactive because its surface is covered by a thick, insulating dust layer. Another is that it is a rocky asteroid that was somehow scattered out from the inner solar system long ago and is now falling back in, though that path is dynamically hard to arrange. A third possibility, more speculative, is that V1 is in fact related to 3IATLAS, and that the simple backward integration that points to the Oort cloud is missing non-gravitational effects, such as thrust, that changed its motion after leaving the main body. Loeb is not claiming that this third option is correct. His main point is that the case should be checked. To do that, we need better data on V1, more precise positions, better light curves, and deeper images, measuring its rotation period, searching for any small coma, and taking spectra could quickly reveal whether it behaves like a normal comet, a rocky asteroid, or something harder to categorize. While this is happening, 3IATLAS itself has continued to show a complex pattern of jets. A November 8th image by Michael Yeager, Gerald Riemann, and Enrico Prosperi revealed at least 7 distinct jets fanning out in different directions. Some point roughly toward the Sun, some away, and some at angles that do not match either direction simply. If each jet marks a preferred direction in which material can leave the nucleus, and if a significant fraction of the comet's mass, on the order of 10 to 20%, was ejected near perihelion, then the total amount of material carried into space could be several billion tons. If that mass is mostly dust and gas, it would remain a diffuse cloud. But if part of it is concentrated into large chunks, with masses of millions of tons each, you could imagine dozens or even hundreds of individual bodies being launched along slightly different paths. Most of those bodies might be too small or faint for us to detect at current distances. A few, especially the larger ones or those whose motion takes them closer to Earth, could be seen with deep imaging and careful searches. This is one more reason December 19th matters. When 3IATLAS is closest to Earth, searches for faint companions around it will have their best chance of success. We would not only point narrow, high-resolution instruments at the main coma, but also run wide-field surveys that cover several million kilometers around the nucleus. Any mini-objects would move slowly against the background stars, and repeated images over hours or days could reveal them as shifting points of light. Once such objects are identified, if they exist, their paths can be tracked. From those tracks, we can test whether they are simply drifting under gravity, or whether they seem to maintain special formations or steer in ways that random fragments would not. That kind of analysis is challenging, but it is the type of measurement that could clearly distinguish between natural debris and controlled probes. All of this work, deeper imaging of 3IATLAS, monitoring of V1, wide field searches for companions, requires observing time, coordination, and funding. Proposal reviewers and time allocation committees must be convinced that the questions are worth the effort. Many in the community still believe that 3IATLAS, V1, and related phenomena stand within the wide range of natural behavior, even if they are unusual. From that view, treating them as likely probes may seem like a distraction from other priorities. History reminds us, though, that scientific consensus can shift. Ideas such as continental drift, black holes, and the accelerated expansion of the universe all began as uncomfortable suggestions that did not fit accepted models. In each case, they moved from fringe to mainstream when enough solid evidence accumulated. Loeb's work on 3IATLAS tries to play a similar role, not by claiming certainty, but by pointing to data that standard models handle only with difficulty, and by arguing that we should be open to the idea that our first picture of this object might be incomplete. He has received strong criticism for this stance. Some colleagues see his public statements as too bold, too likely to feed sensational headlines, but the calculations in his papers are based on observed light curves, measured orbits, and basic physics. You can disagree with his interpretation without dismissing the underlying questions. The key point is that 3IATLAS and possibly V1 present us with a set of measurements that do not slide smoothly into existing categories. When that happens in science, the safest approach in the long run is not to ignore the tension, but to examine it more closely. The universe is under no obligation to match our early expectations. If 3IATLAS and any companions turn out, after careful study, to be purely natural, we will have learned more about what icy bodies from other systems can do. If they turn out to be something else, the implications will be even larger. Either way, taking the evidence seriously and following it wherever it leads is the only way to find out. From here, the practical question is simple. How do we actually follow the evidence while the object is still within reach? 3IATLAS is on its way out. By early January, it will already be noticeably farther and fainter. By the time it passes near Jupiter in March, detailed observations will be far more difficult. Around the middle of 2026, it will be too distant for any realistic follow-up. If the key measurements are not made in the next short interval, they probably never will be. The result would be years of argument built on incomplete information rather than on a solid observational record. So far, humanity has confirmed only 3 interstellar visitors: Oumuamua, 2I Borisov, and 3IATLAS. The next one may not appear for decades. There is no guarantee that the next will be brighter, nearer, or easier to study. In that sense, 3IATLAS is not just another comet in a long list. It is one of a handful of samples from outside our planetary system, and possibly the most interesting one so far. There is also a practical clock. The sideways jets that triggered much of the recent discussion were first clearly seen around November 20th. From that date to December 19th, the time of closest approach to Earth is a span of only a few weeks. During that time, any mini-objects associated with those jets will drift farther from the main nucleus, but not so far that they cannot be linked back. It is in this window that wide-field searches for companions, high-resolution imaging, and detailed spectroscopy have the best chance of giving clear results. In professional astronomy, however, telescope time is planned well in advance. Large facilities like Hubble and James Webb operate on schedules arranged months or even a year ahead. Proposals are submitted, ranked, and fitted into crowded timelines. To interrupt that system and retarget major instruments toward a newly urgent object requires special justification. Committees have to agree that the scientific case is strong enough to override other projects. For a target like 3IATLAS, whose basic nature is controversial, that is a high bar. Many astronomers still expect that once everything is modeled correctly, its behavior will fall within the wide range of natural comet physics. From that perspective, using scarce time on premier telescopes to test a low-probability artificial hypothesis seems risky. It might displace other work that is almost certain to produce solid, publishable results. Loeb's argument is that the usual risk calculation does not apply in quite the same way here. He notes that before 3IATLAS was discovered, the chance that an interstellar comet would display a dozen separate anomalies, including a persistent sunward antitail and an X-shaped jet pattern, would have been judged extremely low. Yet such an object does exist. Reality has already outrun earlier expectations. He also emphasizes that the observations required are not technically exotic. Measuring jet velocities through spectroscopic Doppler shifts is standard practice. Imaging the coma at high spatial resolution is something Hubble and other telescopes do routinely for comets and asteroids. Searching the region around the nucleus for additional moving points of light is exactly what survey telescopes do every night when they look for near-Earth objects. The tools exist. The difficulty lies in convincing institutions to use them on this particular case at the necessary scale and in the necessary time frame. Behind that difficulty sits a familiar principle. Extraordinary claims require extraordinary evidence. Most scientists agree with that. Where Loeb pushes is on the second part. Extraordinary evidence usually requires more than ordinary observations. If we never commit the best instruments to studying the most puzzling objects, the record of evidence will always fall short of what would be needed to seriously test unusual hypotheses. In other words, we cannot demand decisive evidence and then decline to collect the kind of data that might provide it. At the moment, the evidence for artificial origin is suggestive, but not decisive. There are multiple features that strain standard models, but none that force a technological conclusion. To move from possibility to probability, clear tests are needed. Jet speeds, thermal maps, resolve structures, companion objects. Those tests are exactly what December's geometry allows us to attempt. That is why the coming observing window carries weight beyond a single object. It will show how willing the astronomical community is to respond quickly and openly when something fundamentally odd appears. If a coordinated set of observations is mounted using space telescopes and ground-based facilities, narrow and wide fields, spectroscopy and imaging, then, regardless of outcome, the record will be rich. If, instead, only limited or incidental data are collected, the chance to narrow the possibilities will pass. The possible outcomes, in broad outline, fall into a few categories. If 3IATLAS continues to behave like a very active but otherwise natural comet, with gas speeds in the expected range, temperatures consistent with solar heating, compositions dominated by known volatiles, and no discrete companions that behave in non-gravitational ways, then the artificial hypothesis will weaken. The anomalies will still need detailed natural explanations, but those explanations will seem more plausible if nothing explicitly points beyond known physics. If, on the other hand, observations reveal clear technosignatures, jets moving far faster than sublimation allows, long-lived fragments following guided paths rather than ballistic ones, infrared emission inconsistent with sunlight, or materials that cannot be produced in a simple icy nucleus, then the interpretation would shift sharply. Multiple independent groups would need to confirm such findings, and any announcement would likely be cautious. But the data themselves would be hard to ignore. A third possibility is that the results remain ambiguous. Data might support both very stretched natural models and speculative artificial ones without firmly deciding between them. In that case, discussion would continue, perhaps for years, with different teams emphasizing different pieces of evidence. This uncertain outcome would be scientifically honest if the measurements simply do not discriminate strongly, but it could be difficult to communicate. It is in that gap between measurements and clear conclusions that public trust is often tested. Part of the concern about how this story unfolds is not purely scientific. It involves how data are shared and how much of the reasoning is visible. The recent government shutdown and the delayed release of some images already created a feeling, in some quarters, that information was being held back. Whether or not that impression is fair, it shows how quickly gaps in communication can lead to suspicion. One way to counter that tendency is to make observations and analyses as open as possible. Rapid release of raw or lightly processed data, clear statements of what is known and what is still uncertain, and peer-reviewed work that is accessible rather than hidden behind paywalls all help. They allow independent researchers to test claims, reproduce calculations, and explore alternative explanations in public view. Loeb has chosen to share much of his reasoning openly, through preprints and public posts that show intermediate steps as well as conclusions. That approach has exposed him to criticism, but it also allows others to check his numbers. Whatever one thinks of his preferred interpretation, the trail from observation to inference is there to be examined. The broader scientific community now faces a similar choice at the level of institutions. As the key dates pass and new sets of spectra and images are taken, they can either keep the details within small teams until every conclusion is polished, or they can let more eyes see the data earlier. The first approach reduces the risk of premature or incorrect interpretations, but increases the risk that others will suspect important facts are being filtered. The second approach invites messiness, but builds trust that no single group controls the narrative. Whatever decisions are made, 3IATLAS will pass on. Its path through the inner solar system is brief compared with the time it has spent in interstellar space and the time it will spend there again. Our chance to watch is a thin slice of that journey. It is also a test of our willingness to adjust our ideas when confronted with something that does not fit neatly into familiar boxes. If, after all the work, 3IATLAS is shown to be a natural comet with extreme but understandable behavior, that will still be a valuable result. It will extend what we know about how icy bodies can behave when they come from other systems. It will highlight new roles for volatile ices, internal structure, and jet dynamics in shaping comet evolution. If the outcome points in a different direction, toward engineered structures or guided motion, the implications will extend far beyond comet science. Questions about communication, intent, and long-term monitoring of interstellar space would move from speculation into practical planning. Even then, the first step would be the same as it is now. Measure carefully, compare models, and let the evidence guide the next questions. In all scenarios, the core task remains the same. Look closely while the opportunity exists. Use the instruments that can genuinely distinguish between competing explanations. Share enough of the process that others can follow and critique it. Accept that some answers will take time to emerge. 3IATLAS, with its odd jets, its possible companions, and its unusual orbit, is one case study in how we respond when the sky offers something unexpected. The decisions made around it about what to observe, how quickly to share, and how open to be about uncertainty will echo in how we handle the next interstellar visitor and the next after that.